Hey, I wanted to stretch what you already know about kinematics a little bit more and show you the calculus side of it. Last time we did the algebra side, we had the three big formulas, the velocity formula, v equals v naught plus at. We had the displacement formula, x equals v naught t plus 1/2 at squared. And we had that velocity squared formula, velocity squared equals v naught squared plus 2ax. You need to love those things. You need to have them on your card. That is the heart and soul of what we're doing for test 1 in here and being able to solve those problems. However, there's a little bit more that we can do with that with calculus, and so I wanted to talk to you about that a little bit today. The first thing here that I want to do is kind of draw some graphs, and I'd like to tell you a little bit of story. Here, down here at the bottom, is little Timmy's house, and up here is the grocery store. All right, now these wouldn't be one above the other. I've kind of changed the axis here. We're graphing the position on the y-axis and the time on the x-axis here, and as the time changes, little Timmy is going to ride from his house to the store. His mom said, go get some eggs. Okay, he jumps on his bicycle, and as time moves to the right, he's getting farther and farther and farther away from his house. Okay, and he finally makes it to the store right there, and he stops for a little while, and then he starts heading back toward home. And then he remembers that he didn't actually get the eggs. He stood there and read a magazine or Archie comic or something. So he goes back to the store, finally gets the eggs, and goes home again. All right. The x-axis here, which is on the y-axis, right? But the position, his position, graphing that as a function of time, shows that he went to the store, that he started back, stopped, went back to the store, and then went home. Like that. So there's several things that we can learn from doing a graph like this. One, we can see the story, see what happened, and that he started back and had to stop and turn around and everything. We could think about the slope of this line. As I'm right here, you can see that the slope of that line is pretty steeply up. While he walks in the store, doesn't look like he was there a huge long time. Maybe I should have stretched that out a little bit longer. But I've got a slope of 0 right there, and then I've got a slope that's negative here. He's headed back toward the house. He has to stop and think about whether he's actually going to get the eggs and fess up that he just read a magazine. And then he realizes he better go back and get the eggs because otherwise his mom's going to be ill at him. But right here, he's got a positive slope, and he goes, gets the eggs, pays for them, and goes back home. Looks like that's not quite as steep as the other one. Now I'd like to get you to think about this slope for a second, remembering that the slope is equal to the rise over the run. And the rise here would be what's happening in the vertical direction. That's the change in x. And the run, the horizontal axis, is how it's changing in time. Okay, so I got a delta x over delta t here, and that would be the slope of that curve at every point in time. And that slope is a measurement of his velocity. The velocity, how fast he's going. The steeper this line goes, the faster he's riding. So he's riding all out right here. He's with the wind. And then right there, the slope is 0. His velocity is 0 as well while he's in the store. These 2 times. He actually had to stop here and kind of think about what he was doing. But he rode all the way to the store. That's a positive slope, positive velocity. He turned around and came backwards, changed his direction. The slope is negative there. So that would be negative velocity, or velocity in the other direction. Put backwards. I think you know what I mean there. Here his velocity is forward, positive slope, and negative again as he heads backwards towards home again. And so just kind of think about that. Now, it wouldn't hurt to to know that this negative sign, where I have a positive slope and a negative slope and all that, that's indicating the direction. I'll put a big plus right here and a negative right there and a plus right here and a negative over here. One of the deeper things that we kind of do is that a sign in physics always indicates direction. So when he's got a positive velocity, that would be velocity in one direction, and a negative velocity would be a velocity in the opposite direction. If I put a pot on the stove, the heat from the stove is going into the pot, so I could call positive heat that heat that's going in. Meanwhile, steam and heat is coming out the top of the pot. That's leaving, that's subtracting the heat, so that would be a negative. Anytime you see a positive and a negative sign, it merely means direction in physics, and it's not a big deal. We'll learn to deal with that. Okay? So the velocity is equal to the change in position over the change in time. That's an algebraic expression. That's nice. We did that last time. I think what we wrote last time was that the average velocity was equal to the total distance over the total time. That's kind of another way to write the same thing. But here's where I'd like to stretch it. Instead of those deltas, I'd actually like to put a dx dt. I can come through here and say the velocity is equal to the derivative of the position as a function in time. Now, I didn't go into the gory details of this word right here on that first video. The 201 people don't really need to know the distinction between that. But displacement is a little bit different than distance. Distance says how far did you go? How far did little Timmy travel here? And that's one number. The other number, though, is the displacement. And that would be how far away from home did he end up? How far away from the starting position? And if you look at these two numbers, they're not necessarily the same thing. If I measure the distance from the house to the store, let's just make up a number. Let's say that's 2 miles. All right. That would be the distance. When he rides from the home to the store, his distance is 2 miles, and he's 2 miles away from home, so his displacement would also be 2 miles. All right. In that case, they are the same number. But what if he rides from his house to the store and back to his house? In that case, I'd have 2 miles going this way, and then backwards 2 miles, and I could really call that plus 2 minus 2. The displacement would be 0 in that case. Now, I guess what I should write is, here's a red arrow going this way, so the distance is 2 miles, and the displacement is also 2 miles. That one is the same. However, when I come in here and think about the round trip thing, when he goes there and then back, the distance would be 4 miles, but the displacement, he's right back where he started. The displacement would be 0. Okay? When I measure from the beginning point to the ending point, if he makes it back home, then his total displacement is 0. All right? So that's kind of a little subtle twist on that word displacement right there. It's not a big deal. X measures displacement. It doesn't really measure the distance. It measures the displacement. All right? So kind of keep that in mind. What we've seen here, though, is that the velocity can be written as a function of the displacement. And specifically here, it would be the derivative of it. So anytime I have a function of displacement, let's say that the displacement is 2t plus 7. If I want to find the velocity, that's super duper easy to do, because all I have to do is take the time derivative of the displacement. Most of these are polynomials, so they're super easy derivatives to do. If I take the derivative of 2t plus 7, I just get a 2. His velocity would be 2, and that's kind of understood to be meters per second. I left the units out up here just to keep it simple. But we'll tack on the meters per second there. And over the course of this whole thing, again, I just made up these numbers, so that may not be quite the right number, but you get the idea, right? The derivative will give me the velocity. If I have a function for the displacement, I can take the derivative and get a function for the velocity. All right, so that's the first thing. Here's kind of that rule. Here's another example, right? They say in this case that the position or displacement is 3t squared minus 2t plus 7. You want the velocity? No problem. Just come in here. We need to take the time derivative of the displacement, and that's going to be the time derivative of all that stuff there, 3t squared minus 2t plus 7. Again, it's a polynomial. This couldn't be any easier. You take that 2, you multiply by the 3, so that'd be 6. There's a t to the second, so I need to drop that down to t to the first. Take the exponent times the coefficient, lower the exponent. Right here, move on to the second term. This is really a t to the first, so 1 times negative 2 would be negative 2. And I've got that t, it was 1. I drop it 1 space, 1 down, 1 minus 1 would be 0. Right here, this could be written, oh dear, could be written 7t to the 0. Okay? T to the 0 is 1, so that's the constant term on the back. But 0 times 7 is 0. And that's why that thing just disappears, goes up into smoke. I could simplify this. 6t minus 2 would be a function that tells me how fast I'm going at any point in time. You tell me 2 seconds, 5 seconds, 10 seconds. I can plug that number in there and saying at 10 seconds I'd be going 58 meters per second or something. So this is kind of an important thing. It's a short step right there. It's already delta x over delta t. Just change the deltas to d and you got yourself a calculus function that works really nice. All right. Now, this was little Timmy on his way to the store. He stops and goes in. He turns around and comes back. We've already said that the slope of this line is positive, and here it's 0, and here it's negative, and here it's 0, and here it's positive, and here it's 0, and here it's negative. Okay? So what I'm going to do is to graph those. I'd like to come in here and say his velocity is positive right here. So let's just put something about there all the way up to this point right here. Let's actually put it about right there. Give him a little bit of time in the store. There's the time that he's in the store. So his velocity was positive. This would be my velocity axis now. And came along. When it gets right here, it's going to drop to 0. Oh, man. Thought I had all the tools worked up, and this was going to be super nice. Let's see what's going on here. Draw me a line. Would that be so hard? Anyway, it goes to 0. Whoops, sorry, too far. For that little piece right there. And then it actually goes negative. So I'm going to draw this thing as dropping down into the negative region here. And it goes over to the point where he stops and thinks about whether he needs to go back and get the negative. Well, this just sucks. Right there. Okay, that's when he stops. So at that point, his velocity goes to 0. He's back at the axis there. He says, "Fine, I'll go back and get my eggs." He's got positive velocity over here. He goes into the store right here. So his velocity would be 0 right there. Comes out of the store, gets on his bike, and he's got a negative velocity there. I'm kind of guessing. Looks like his looks like it's not quite as steep here as it was over here. So I'm actually going to draw this line maybe a little bit still negative, but not as negative as it was before. All right. So the graph would do something like that. I'm going to try to draw this, but I don't think it's going to let me. Let's see if changing colors helps at all. The graph of that velocity would start here, and he goes across with a positive velocity, and it drops to 0. He's not moving while he's in the store. It goes negative. Then he heads back, so that's a negative velocity. He stops, has 0 velocity while he thinks about it. You get the idea, right? So that green line is a graph of his velocity. And I can just read the value off of that and see what that looks like. Now, not all functions are straight lines, right? These are kind of chunky here because he rode 2 meters per second or whatever the number is to the store. He stopped and it was 0, and then it was -2, and then it was 0, and then it was +2 and 0, and then let's say it's -1 over there or something like that. I could have a function of time that had you know, something more like that. And I could go through the same argument that we did before and say, well, here I have a positive slope, and here I have a 0 and a negative slope, and all of that. And we could write the same thing that we did before. We could say that the slope is equal to the rise over the run. And when I look at the rise, I'm no longer graphing x. Now I'm graphing velocity as a function of time. So this would be the change in velocity over the change in time. And what we're going to do again is to flip that so that it's dv dt. And you know that the change in velocity as a function of time is the acceleration. So the takeaway here is that acceleration is equal to dv dt. All right. We already had that v was dx dt. So here's the one we had. Now we've got another one right here that looks like that. And those two together, if you know a function of time that gives the position of an object, you can take the first derivative, get the velocity. You can take the second derivative or take the derivative of the velocity and get the acceleration. That's kind of neat. Here is that written up. They've given us an example here. So the velocity is 6t minus 2. If I want the acceleration, right, I notice that this is a function of time, right? See how it's got that t in it? In the kinematics video, that first video, well, not the first one, we had the math review video, but in that kinematics video, we just had a list of numbers, right? We had x equals 4, and v0 was equal to 2, and time was equal to 6, and what's the acceleration, or something like that, right? And we would solve that. If it's just numbers, do the algebra. Algebra. Okay? On the other hand, if you've got a function of time, that's where you can come in and do the calculus, of which so far we've got two kinds, right? v equals dx dt and a equals dv dt. Okay? Well, this is a function of time. I see that expression there, 6t minus 2. I go, that's a function of time. I bet I'm supposed to do some calculus on this. And in fact, I know that the acceleration is dv dt. So that would be the time derivative of 6t minus 2. And that's pretty easy derivative to do. You just get 6, right? If you want the gory details, this is t to the 1. 1 times 6 is 6. Drop it, you got t to the 0. Over here I had 2, which is really negative 2t to the 0. 0 times 2 would be 0 times t to the negative 1. But 0 times anything is 0. It goes away. This is a 1. I just end up with that 6 right there. Okay? So you can take the derivative if you have an expression, a function of time, and that's easy. All right? Now, we can go the other way. What we just saw was here was a function of time that gave the position. We took the derivative, and we got the velocity. we took the derivative again, and we got the acceleration. Sometimes the problem will say, well, here's a position of time, here's a function of time. I'd like to know what the position is after 15 seconds, after 3 seconds, whatever the number is, right? So see how it's real easy to just come in here and say, well, fine, x equals x at 3. And I could just take the 3 and put it in there. I'd have 3 times 3 squared minus 2 times 3 plus 7. If they give you a single function, say, give me the value of that function at time 3, then you just put the number in. It's not a big deal. You go, well, that's 27 and minus 6 and plus 7, and that's going to be 1. So I got 28 here, and it's x, so this should be meters, and put it on there. It's okay if they give you the units here to chase those through. It's easier just to go x should be meters, v should be meters per second stuff. All right. So again, if they give you a function and give you a time and say, go get me the value of x of that same variable, then all you got to do is plug the number in. However, if they say, here's a function x, I want v, the next one down, I got to take the derivative. We did that. If they say, I want the acceleration, you got to take the derivative of the derivative, or the second derivative. So that's fine. But what we really want to do here is to go backwards. What if I knew this was the acceleration? Could I undo that derivative and come back here? Could I do the antiderivative? Yeah, sure. The antiderivative is the integral. So we could do integration here. And we could say v equals the integral of a with respect to t. And I could go from this one to this one. I had to do the derivative to go from here to there. So if I do the integral, again kind of going backwards, x equals the integral of v dt. So these are the companion rules to that. And I can go either way with it. If they give me a displacement function, I can get the velocity and the acceleration. Or if they give me the acceleration, I could get the velocity and the position with the integration. Now, if you want to see the gory details of that, it looks like this. What happens is, let me just write the derivative. When we said that velocity was dx dt, okay? And people play loose and fast with these differentials dx and dt. So if you treat it almost like algebra, this isn't really right, okay? This isn't really good math, but people rearrange this to say v dt is dx. It's almost, it looks like you multiply both sides by dt. That's not what's going on here, because this is a notation. It's not an algebraic expression. So whatever. But I could come along and integrate both sides like that. And on the come back. Thank you. All right. I'm going to just leave the left-hand side alone. Have the integral of v with respect to t. The integral of dx would be x. All right. So that, you know, this leads me directly to there. That's this thing over here once I flip it around. And so that's how those get cooked up that way if you want the gory details. All right. Let me just do this real quick, and I think you'll see what I mean. Let's take this function right here. They say, I'm hoping I have enough room to finish this up here. Getting a little tight. A function of time is 6. All right. So if I want to get to v, then I would have to integrate 6 with respect to t. And of course, when I do that, the 6 is constant. I could pull it out front, and I'm integrating dt. So I just get 6t. But you know that I'm supposed to add a constant of integration right there. So that would look like this. All right? And I could get back. That's not quite 6t minus 2, but I do have the 6t plus or minus something, right? And so I'm getting in the right ballpark. And what I've got to do is take some kind of initial condition up here at the top. They say, well, at time 3 seconds, I was moving 16 meters per second. So if I take those two numbers and I put them in down here, the velocity is 16 when the time is 3. And there's that plus c. See how easy it is to come along and solve for c? They got to give you an initial condition here so that I can get the specific solution of this thing. But it's not hard to do. You just plug the two numbers they give you in. Down here, 6 times 3 would be 18. Subtract 18 from both sides. Negative 2 equals c. And then I'd take that right there, and I could plug it back into my general solution for this thing, and I would have v equals 6t plus c, which was really negative 2, and I'd have the whole thing back again. 6t minus 2 is what we had right there. And I could use this guy, and I could cook up the position over there, and I'll do that real quick in the little bit of space that's left. We said that x was equal to the integral of v dt, so that would be x equals the integral of my velocity. I just got it down here, 6t minus 2. Integrate that with respect to t. I do the integration, super easy integration, 6t squared over 2 minus 2t. Again, I've got to add a constant of integration because I don't have any limits here. And so I put those in. The 6 divided by 2 would be 3t squared. Here's a minus 2t plus c. I don't know what it is yet. So I've got to come back up here, and I got to say, well, the time is 3 seconds, and the position is 28 meters. And I could put those in. I could say 28 equals 3 times the time is 3 minus 2 times 3. Here's my plus c, and I could solve this thing for c. Now, if you want to call it c2 or something like that, because we have two limits of, or two constants of integration, that's fine. Okay, if you want to give it some other name, knock yourself out. But the point is, it's not hard to come through. 3 times 3 times 3 would be 27. I subtract that from both sides. I'd have a 1, and then I've got to add a 6. 1 plus 6 would be 7. So I would get my constant of integration is 7. And I'd add that back in. I'd replace that constant of integration right here with plus 7. And you can see that that's exactly what we have right there. Okay? So that's the whole thing with doing this calculus kinematics. It's not hard to do. You've got 4 tricks here. Right there, they all are. If they give me position, I can get the velocity. If they give me velocity, I could take the derivative and get acceleration. Or, if I have velocity, I could integrate and get the position. And if I have the acceleration, I could integrate and get the velocity. All right? So that's pretty straightforward. And try a couple of those. Just cook up any kind of polynomial that you want. And it should work out fine. It's also, sometimes you'll see the position given as let's say that the position is equal to the sine of t, right? Maybe I have an object that's starting here, and it's oscillating, it's going back and forth. Like, so this thing is going up and down like a sine wave would, and that's a crummy sine wave. Okay, but I could take the derivative. Let's see, I'm sorry, I'm over here. Yeah, that's my position. I could take the derivative of that and get the velocity. Take the derivative again and get the acceleration at any point in time. If I knew the velocity, you get the idea, right? So if it's something other than a polynomial, just do the regular derivations and integrals on it, and you've got your stuff. All right. Well, that's the end of the calculus kinematics video. If you have any questions about that, just bring it up in when we meet on Zoom or in class or wherever. And hope you have a great day. Thanks.